much. First, I would really like to thank the organizers for the opportunity to some extent come back home again. If you calculate my time in Scandinavia between sabbatical leaves and invited visits, my family and I have probably spent about 5 years over here, and they were some of the most impactful times of my research career, and actually for my family itself. Okay, let's see if I get this right. So right now, I'm a governor's chair at the University of Tennessee. That's my formal employee, and my time is split between the Carbohydrate Research, Carbon Renewable Center and Chemical Engineering, and then Oak Ridge purchases 50% of my time. So I have 50% of my time in my group over at Oak Ridge. There was two things they told me. Do not get lost in technical jargon and stay at 15 minutes. Of those two, the latter one is really hard for me. Okay, so way back in 1989, I started my career. If you wanted to do work in lignocellulosics, in those days it was pulp and paper or lumber. The only research my mother and father ever understood of me was brightness reversion of mechanical pulps. Why does newspaper turn yellow and how to stop it? And as a career, I went from that to ECF, TCF. Bleaching was an environmental issue. We did work on craft pulping yields and cost, fiber modification, and we did some packaging studies. And then, in my case, the market kind of changed. And what I mean by change is all of a sudden society became interested in climate change and its impact on our lifestyles across the planet. And we all know these weather things. We also know that, in essence, the temperature is continually increasing, and I think most of us in this audience would agree this is due to the carbon emissions that we have decided to pump into the environment. And it all depends what we do here, what your friends and family do. If we do nothing, the temperature is going to continue to exceed. If we can drop our amount of carbon discharges, we can decrease in climate temperature increases by either 1.5, 2.5, or less. And we started our career in this in 2006 when we published an article in Science on the biorefinery. From there, now on this side of the ocean, there's not much argument that there's a relationship between the CO2 and the environment and the climate change itself. But in reality, if we forget the scientific arguments, if you just look, I remember when I came here in 1995, there was no air conditioning in Europe, and there was none in Scandinavia. The demand for AC has gone up. The demand in my home country, Canada, has actually gone up. Now, it's saturated in the US, so I don't bother to plot it. But not only are we, as humans, looking for cooler climes, if you project out what happens as the environment heats up, mammalian systems, animal systems are going to move north, simply because they're looking for cooler climes. So in all of this, what's come out of it is an agreement in society to try to pursue the vision of basically net zero, that we're not going to, the amount we dump in plus the amount we take out, we don't increase the amount of carbon in the environment. 30 countries that have decided we're going to do this. They're in different stages of we're going to do this. I was extremely pleased when I stopped in Munich. Lo and behold, there's a sign that the Munich airport is actually going to go to net zero by 2050 also. So it's indicating that not only is it a governmental policy, but it's slowly starting to go into practice. If you look at, let's see, one more click, I hope, yeah. In 2021, we had about 10 countries that had agreed to implement net zero by 2025. There's a series of others that have positional papers and others that are entertaining it. Last week, I was over in Singapore. Their government has announced that there'll be carbon net zero by 2050. And to do that, you're going to need to do research to implement that vision. Let me go back one, I'm sorry. Well, maybe I don't want to go back one. Let's see. Try it once more. If, as a planet, we agree to pursue this, then the CO2 emissions, both from industrialized nations and emerging and developing nations will have to drop dramatically. You get down to 2050, but both of them have to come down. And to some extent, some of the industrialized nations are easier because we've already offshored some of the most carbon-intensive industries to emerging markets. Unlike 10, 15 years ago, no, more like 20, when we started our work in biofuels, and the focus was just to make biofuels to reduce the emissions from transportation, if you truly want to move to net zero, then you have a host of industrial sectors, heating and cooling, cement, road vehicles, power, steel, airline, shipping. All of them have to participate in this. It's not, well, we'll let the other guy do it. Everybody has to participate, because in essence, at the minimum, to stabilize us at 1.5 degrees C, I think it's 10 gigatons of carbon you're going to have to take out. Oh, okay. This is crazy. Let's see. No, I apologize for this. So, when I go to recruit incoming graduate students for research in biofuels, this slide is always the killer slide. Why am I interested in doing biofuels? Because Tesla is going to solve the whole world's problems. Always comes up. In reality, it's not going to. For us to get to net zero, biofuels have to be part of that value proposition. Yes, well, some of it will be electrified. Those of you that have greater sensitivity to U.S. demands, you can see that all the major manufacturers are having problems selling EVs right now, and there's more interest in hybrids than there is in EVs, and that's just consumer pushback. Until battery technology evolves forward and there's greater charging, it's not going to happen. So you're going to have greater diesel production on bio-based diesel. I'm going to come back on that in a minute. And then clearly there's going to be a dramatic growth in biofuels for SAF, sustainable aviation fuel. And we don't eat enough French fries, and at least in my case, I shouldn't. There isn't enough grease in the cooking grease to propel all those planes that are flying across the world. There is another unique thing where we really differ, North America, from you guys. Our distances are vast, okay? And about 72%, yeah, that's right, 72% of our transportation of goods goes by truck in the nation. And if you do that, and you say, well, okay, we'll offload that to batteries. Well, right now, you're going to get about 500 miles per charge. And if you're going to ask a trucker to do it, whereas if he fills his tanks with diesel, he gets about 2,000 miles per tank full. Nobody is going to do 500 miles per charge for transnational shipping in the U.S. Will they do it intercity? Sure. That's not a big challenge. That can be done. But the big challenge is to ship it across. Now, if you're shipping in Norway, and you got mountains, let's say France, it's not that far. You could probably electrify it. But if you're going even intercontinental Europe or further, diesel's still the way to go. To address those carbon challenges, you're going to have biodiesel. And then if you look at oceanic requirements, most people believe close to shore, tugboats and that will be electrified. Transoceanic, biodiesel, perhaps biomethanol may come into play. Excuse me. When I was in Singapore, the big push there is actually to use ammonia. They're thinking of importing it from Australia and then utilizing it as a fuel themselves. But they also acknowledge that a bio-based bunker fuel is an equally promising alternative to petroleum bunker fuel. And then where we have a research program right now in the U.S. and in some of the major ports, they have sulfur emissions, and the bunker fuel, which is the cheapest, dirtiest fuel you got, has got sulfur in it. So we have a program using biomass to diminish those SO2 emissions. And all of this is a tremendous amount of fuel energy costs to replace. The recent billion-ton report that came out in 2023, which is the third version, confirmed that the U.S. as a whole has about 1.2 billion tons of biomass that you could use that's available for conversion to stuff, let's say. Nowadays, it's all petroleum-based largely. The amount of bio is a small component, but you can see in the slides that the biodiesel light transportation will be electrified, but you'll still have some, and then you have aviation that has to move on. And that will be wood waste, but it'll also be, because the U.S. has tremendous agricultural potential, agricultural residues, and some energy crops. So then if we go back, this is an old review, but I love the way it just simplifies everything. You got two platforms. You got the bio-based platform, or you got a thermochemical conversion platform. And we actually do research in both of those. I'll walk you through some of this. You heard several talks on using nanocellulose. The top part of this slide I use for recruitment, and I even use it in my high school talks because it's really nice. I bring a piece of lumber in, and then I bring a piece of wood chip in to the kids, and then some fibers, and they can visually see all these components. So we have a focus on using on nanocellulose in our program. Come on, hurry up. And if you use an acid condition, you can get to CNCs. If you use mechanical high shear, you get to nanofibrillated cellulose. The one unique aspect of our work is that most of us in the community, and so do we, use a virgin kraft pulp or a recycled pulp, but that's still an expensive feedstock. I haven't looked at pulp prices lately. The last time I saw, they were about $900 a ton. Recycle gets you down to $150, $200, depending on what you're recycling. But if you use wood, then you can get even a lower cost, $40 to $70 a ton. So we've been looking at making lignin-rich CNCs and lignin-rich nanofibrillated cellulose, or lignocellulosic fibrillase. And we stick these in composites. We also stick them in a variety of inorganic materials and utilize that to build up order and improve physical properties. Way back when, the first time I was over at Chalmers, I did work with Paul Gottenholm, who loved xylane. I remember once he took me to his summer house, and we walked down to the beach, and he pulls out some seaweed, and he goes, "Look, this is nothing but xylane. Can't you do anything with this?" And actually, since then, we've been making a host of functionalized xylane films and showing that you can incorporate nanocellulose in there to improve strength properties, reduce oxygen and water transmission. I had thought we'd finished our contribution on that, whereas recently we've been approached to use that same thing as an approach to barriers, to improve the barrier properties of paper packaging. The other thing, when I was still at IPST, Institute of Paper Science Technology in Atlanta, we had done some work with Procter & Gamble, and they had a cross-linking technology for cellulosic fibers to make them more water-absorbing. And one of my students came in late one night and showed me the smaller the fiber she had, the better the water absorbency properties were after cross-linking. So I said, well, why don't we use the smallest fiber we can? Let's use CNC and see what happens. And that's been a program ever since, because we've come to realize if you cross-link nanocellulosics, depending on cross-linking density and what you use to cross-link, you can get a foam, you can get a gel, you can get a plastic in itself, and you can tailor the physical properties. The other thing, you know, when I tell people we use cellulosic fibers, they're, well, it's kind of boring. It's, you know, you're making paper. What's new in there? But, you know, in reality, there's a lot you can do without having to use the word cellulose. Sorry about that. Cellulose is incorporated right now into concrete products for a variety of applications. Our house right now is brick, but the last house we had in Atlanta had what was called hardy plank, which is about 15–20% cellulose with concrete. Fantastic stuff. It didn't rot. It didn't swell because of the humidity in the south. And we've been looking at using cellulosic reinforced concrete actually for marine applications. Likewise, on the decking, and you guys don't have this problem in Finland, you don't have humidity. The decking in a southern house in the U.S. is usually made from timber. The problem with the timber is the humidity and temperature swells are such, the wood degrades quickly. So a lot of the siding on the deck itself is usually timber still, but the railing is usually a polyvinyl reinforced with cellulose. They don't do it for the deck because of the load-bearing considerations. Vinyl can't address that. So we've been looking at taking cellulosic fibers, reinforcing nylon, so that you can have structural units. And then finally, just old-fashioned PLA with cellulose gives you a different kind of packaging material. You don't have to worry about water swallowing at all. This is just one nice set of SEM pictures that I got from one of my visiting students from Sweden a while ago, where we can take nanocellulosics and we can order the structure of the final products by doing what's called directional freezing. Let's say this was at 0 and I had a sample in here, I'd put it like this, and then as the thermal gradients go up here and the ice starts to freeze, it expels the nanocellulose, and I get this nice tertiary structure. And we've done some work on that for energy storage and for filtration. But if you actually go in the literature, this is, all the vague right now. You can do it in foams, ion transportation, biomedical, nanocomposites, and continuous filaments. You can functionalize those nanocellulose, and now you can organize the actual structure, and you have a host of applications that the literature is really rich with right these days. Okay, my favorite topic, lignin. When I started, I was assigned this way back in 1989, 1990. And I thought I was like the black goose that just, why study this nasty material? But it turns out it's been pivotal to my career. And it actually, if you're doing biorefining, you come back to the same question Kraft Pulp has had. What do you do with it besides burning? And we have active programs, as many of you do, in materials, chemical utilizations, and fuels. Scott, you gave a great talk this morning. Our love is not the Kraft digester as much as in the sequence of operations in biorefining, where you can either process the biomass, convert it down to simple sugars and ferment, and then take the leftovers, which are rich in lignin. We don't like that because there's a lot of fermentation broth material. There's other stuff in there. You're going to spend more money to purify it than it's worth. Alternatively, you can do a pretreatment that extracts the lignin up front. We've developed a host of tools that allow us to control the DP and the kind of functionalization of that lignin so we can tailor the lignin for applications. And if you go in the literature is really rich with all kinds of applications. You heard someone using it for board, which is close to commercialization. You can make an aerogel, a hydrogel, host of composites. We do a lot with 3D printing, which is really nice, and foams. Some of this we captured and we argued in the literature in our I think it was 2014 paper, that really what was missing at the time is the integration of the natural variants or the genetic capabilities to order the structure of lignin in the starting material and then tailor that towards the needs of the products you have. If you do that, however you isolate it, you must minimally alter that structure, and that's what we do with some of our pre-treatments. And when I started at IPST in 1989, I was told softwoods have a kappa number of lignin content of 33%. Hardwoods are at 22 to 25%. And grasses, forget that, they're not important. So, but we've done natural variant studies of hardwoods where we get anything from 18 to 35% lignin content. And you can use that information if you want to tailor to your product performance parameters. And one of our really promising application studies we have funded out of ARPA-E, we're looking at using lignin to make lignin polyurethane foams. And you can say, Art, what's new? There's a host of groups, and there's a ton of people that publish in that. We have two niches. Our first niche is we are tailoring the structure of lignin by looking at various feedstocks and using the natural variation of lignin in those feedstocks to tailor functional properties of the polyurethane foams. This is using the conventional isonitrile platform. You take the lignin, react it with the polyurethane, make a foam, and you measure your R values. The other way is to actually not use the isonitrile chemistry at all. I don't know the EU policies, but in the US, manufacturing practices are governed by something called OSHA. And if you read the OSHA regulations for using isonitriles, they're hellacious. And rightfully so. It's a nasty chemical. You don't want to breathe it in. You don't want skin contact. So if you could re-engineer making polyurethanes, getting away from the standard way, you have a real benefit. So what we do is we tailor the structure of lignin that we want, put an epoxy group on, and we've done this catalytically, and then we actually react that with CO2. This gives us a carbonate. In old-fashioned undergraduate chemistry, I can take that carbonate, react it with a diamine or a triamine, and I have polyurethanes. The really exciting part of this is, and when it goes back to net zero, is yes, and when we go to program funding agencies, they all say, yeah, I understand biomass is carbon negative, and we'll measure your conversion efficiencies by LCA, but we want a negative value that's even greater than you typically can get from just using biomass. To be able to incorporate chemically CO2 into your material allows us to get substantial savings in CO2 or carbon negativity. The other thing I was telling you about marine fuel, one of the really nice things about the self-pretreatment, which is an acidic THF water pretreatment of biomass, it allows for the extraction of lignin, but we have an incredible fidelity of control over the way we extract it. Charles Kai, who was he's co-owner of the patent for this, he's at the University of Riverside in California, knows this inside and out, and is building a pilot plant right now. But we can either tailor low molecular weight materials or we can tailor high molecular weight materials depending on how he runs that. We take that self-lignin and the low molecular material, we then treat with a copper catalyst in the presence of methanol, which reduces it, and this gives us a SAF precursor on the hydrocarbons. We still get some of the high molecular weight material even when we tailor for low. That stuff can be co-blended with bunker C fuel for marine applications, and that requires almost no chemical modification and drops the sulfur emissions so that they can, naval transportation can actually meet current sulfur emissions right now. What else did I say? Oh, the other thing that's further away, but a lot of fun, we have a lot of people from different parts of the world come see us on this, is that we've taken a series of organisms and asked them, you know, can they use lignin as a carbon source? And Rhodococcus is one. Rhodococcus is an organism that really likes hydrocarbons. You see it frequently in places of the planet where you have oil droppings or there oil discharges. So I had a graduate student, we were on a train from Milan going north in Italy, and we talked about this. He started that program, excuse me, and we've used Rhodococcus and tailored both the biology of Rhodococcus itself and the structure of lignin. And we have certainly shown in a series of publications, too many for this, that we can certainly get Rhodococcus to live off of lignin, that the self-lignin, where we can alter the functionality and the molecular weight of lignin is predisposed to living off of that lignin source, and we get lipids in turn. So it's a way of taking lignin and driving it all the way over to lipids that you can use for biodiesel. And last but not least, on the thermal side, our famous tool that we use all the time is a fluidized bed to pyrolyze lignin. The way we approach this is we pyrolyze either lignin or biomass, and then we have a series of catalysts either in situ with the fluidized bed or thereafter in the gas phase that we can do chemistry to target what we really want. This is just one example of that, where what we're really frequently after is the aromatic component, and we don't want less biochar. We can tailor the chemistry, the types of aromatics, the substituents, try to deoxygenate them as much as possible, and then do a subsequent upgrading. And the last thing I wanted, there's two last slides. We've also done pyrolysis of cellulose. That gives us a set of furan-type structures. And then if you do the pyrolysis in the presence of a rubber, you get diene, so you can do a Diels-Alder, and you can get real nice clean synthesis of substituted aromatics you can use. So there is, instead of just doing pyrolysis, if you engineer the chemistry of pyrolysis along with the catalyst, you can target the exact products that you want. Now, if we don't do this, if you guys don't do what you were talking about all today, what's the alternative? The alternative is the planet's going to get hotter. And already there are startup companies that are saying that they can take carbon out of the environment or out of the ocean by electrolysis of ocean water. There's a whole pile of direct air companies that are starting up, and there's more government studies that are doing this. But the scale is so large, taking out 10 gigatons a year. I don't see why mankind would want to do this approach versus utilizing biomass to address these challenges. Furthermore, the sciences, you start reading it and you start to shake. Or add a whole pile of additives to the ocean so you stabilize bubble growth so you get more reflection of the light back out of the planet. Or build a whole pile of rockets and put reflectors outside of the planet to reduce the amount of sunlight that's coming in. Or whole pile of solar-powered ships that will stick moisture into the air so you get artificial-made clouds. Harvard's actually going to do this soon. They're going to take a set of balloons and drop aerosols at the higher altitudes to reflect light again. And I really can't believe as a race that this is the solution so that we can just burn more petroleum. I refuse to accept that. And all of this, somewhere in the mid-1990s, I had a dear friend of mine who was in the Carlsberg Institute, and we were walking down Copenhagen, and I was really complaining that I just couldn't get in the lab. And she actually stopped me, and she said, "Art, you were great in the lab, but no one's going to pay you what you're getting paid now for working in the lab. And two, you're much better outside the lab than you were in the lab." So truthfully, all the credit to everything I say goes to the people I have the marvelous pleasure, honor, and possibilities to work with. Until COVID, we always had 10 to 14 visiting scientists. Once COVID hit, we went down to 0, and we're going back again. I think it benefits the students, the U.S. students, to see how other people on the planet look at these challenges and how they want to address them. Dear thanks to, most of our funding comes from the Department of Energy. Some of it comes from USDA, who really, pay the bills. And then finally, why am I talking about this? I have a personal vested interest in this. The planet is warming up, and it's warming up the most in the northern and the southern extremes. And the extreme I have a great dear love for the last 14 years, my son and I have gone 500 miles south of the tree line to live off the land, mostly fish. And we've been successful because I've never lost weight on it. But even in those trips, the fishing seasons are increasing. The amount of ice cover that happens, our love is to go fishing immediately after the ice comes on, because that's when the pike mate and they're in the shallow water. 13, 14 years ago when we did this was the second week in June. And some of them are now opening up in May. And the insect populations are changing also. So you may not agree with the science we're doing, but I would champion yours as much as ours, because I think it's an answer that we have to come for mankind. And I really don't want to send up 1,500 rockets with shade to prevent what's coming down the road. I thank you for your time and attention. How was I for time?
Thank you so much. Do we have questions from the audience for Art? Let's see. We have one question here from the chat. So, how do you see the future of sustainable aviation fuels? What are the biggest challenges in their production in large scale?
Cost. It all boils down to cost. Of all the technologies that are happening, I'm involved with one, Thrust, utilization of lignin to make the aromatic component of SAF looks promising. But there's a host of academics and there's a host of industrial people that are looking for the polymerization of ethanol and up. And the U.S. is really good at making ethanol. Brazil is really good at making ethanol. That'll probably be the first stage of commercialization. I mean, you already have the fats, but as I said, there's not enough French fry consumption to address it, you know.
Yeah, that's true. We heard about the Japanese nanocellulose production earlier today. How does it look in the US? I mean, how much do you produce?
That I know who does it, but they don't tell me. I mean, the people that, it was much like Japan. The people that are involved with it, and I know some of it very well because the students graduated when I was at Georgia Tech and moved to these companies. That's all kept confidential, you know what I mean? What I can say is that it's not a pet project. It actually is contributing to their success as a company.
Yeah, that's great. So there was earlier also a question about the magic wand. If you think about all of the research from your lab, if you would be able to push one commercially, which one do you sort of believe most in?
I was talking to Anne about that. When I hear about people and their technologies, and it's more relevant to me because I'm close to retirement, and I ask people, I says, would you be willing to put your retirement money in it? Because usually you take a lifetime to accumulate that. Of ours, it's the polyurethane work. I mean, we have hit all the metrics we put in the proposal, and some of which I was worried about. Our values are fantastic. Not only are our values great, the R values the consumer is concerned with is not the ones you make when it's immediately made, but 6 months, a year later, and our values still are good. We have flammability properties, strength properties, they're great. And the economics we're under current production cost requirements. To me, the real question, because it's all lab-based, we have TEAs that indicates that we can get under what are the current costs. But I think TEA on a lab scale is scary, if you know what I mean, for investment purposes. Our next stage is to do some of this pilot and to see how well it works there.
Is there company interest already towards it? Yeah. Okay.
I mean, one of the things, there are different departments in the Department of Energy. We get a lot of funding from BER, Basic Energy Research, okay? That's a very fundamental focused mission. We also get funding from BETO and from IEDO, which are very applied, which you need industrial partnerships to help you anyways, and those are the ones.
Exactly. Great. Thank you so much,
Thanks.
Art. Thank you.
Appreciate it.